Okay, can you see it?
Yes.
Good. Well, thanks for the IANET people to invite us for this great event. So sorry, I switched back to English, and I propose with this presentation a small journey in a very small scale. I think that's maybe the only presentation looking at indoor scale. So let's go. I'm pretty sure you have seen the increasing interest with depollution system. So that's basically a filter system that takes part of the pollution from the air. And it is quite also often the case that this depollution system is something that is easier to do in indoor than outdoor, mainly because in outdoor you don't have to face the big power of the atmosphere that brings again and again a large amount of momentum and a large amount of pollution. Then when you have a project where you can bring a depollution system, there is some constraint. There is first budget constraint. You cannot bring a lot of depollution system because it can be costly. It can have too large power consumption, and also this kind of system may have also limitation in terms of filtering effect. The filtering is not perfect, so there is some kind of ratio of the part of pollution that can be filtered. Then, with this constraint, the modeling can help to design where to put the different systems in the indoor area. And one of the things that is important is in the two projects I will present, there is local emission, so you need to build emission inventory also in indoor, which is something not well known with not standard procedure as in outdoor field. So you have to find some ideas on how to build your emission inventory. And for sure, for the moment, what we have done is to do some measurements on site to help to fit the emission rates, because there is a lack of knowledge in terms of emission rates and emission factors. That's the first case. So this is a case in the subway of Paris. The project name was IPER. So it's a project from Suez, and actually we have been involved for modeling before the pollution system were set up, and also after, to do some kind of validation. The idea of the modeling was to help to design, but there was a lot of constraint. So the help of the modeling was a bit limited by those constraints. But the idea was also to learn a lot of what we can do and how to set up model for the next time where Suez will be in position to add the pollution system in other subway stations. So there have been 2 field campaigns with mobile sensor, with small sensor, done by Suez, and also the ROTP, which is the administration managing the subways in Paris, has also set up one reference sensor that you can see on the picture here. The air is entering somewhere here to catch the particles inside the system. So on this picture, you see one of the 2 system, the pollution system that have been installed here. So again, this is maybe the inlet, and there should be an outlet on the other side. So here we focus mainly on PM. So Suez have done two measurements with a small sensor at different position in the station to have an idea of what concentration is coming into the station from the different openings, such as the stairs or the train tunnels, and also to see if there is any significant variable spatial variability in the station. Velocity have been measured also at the entrance, at the different entrance and outlet of the station, and also as we need some information about mixing, some turbulence measurements have also been done. In terms of what have been done is to set up a CFD, to use a CFD model. In ARIA, we often use a code Saturn model, which is developed by EDF. And what is important to have in mind is we want to have something quite, even if it's 3D, we want to have something quite simple. In real life, the dispersion of and what is happening in such station is fully unsteady and very complex. And we don't want to bring to go that in this very complex direction. We want to have something quite simple. So the idea is to make the hypothesis needed to have to find something that is compatible with a steady state. Okay, so that means that essentially we have models the movement of the train, the effect of the model of the movement of the train of people with turbulence source inside the domain. And everything is also quite complex in terms of concentration that can enter into the model. So we have mainly used measurements rather than using an analytical value from literature. So basically, you see the geometry, the mesh, and the wind field that have been computed. So it's an average wind field. It's not a particular moment. It's just an average during, let's say, something like 1 hour. And we have set up concentration incoming by the stairs and by the tunnels. And also we have added some emission inside the domain, but it's really difficult to estimate these emission rates. So we have mainly feed them according to observation. So at the end, we have that kind of map. You see that I have hidden the value. Part of the result of this project are confidential, so I cannot give you all the details. So I hope you won't ask so much detailed question after the presentation. Maybe I will say I just not can tell you because it's confidential. So the result of this first case have been a bit used to choose where to put the module, and actually also to choose in which direction we should get inlet and outlet the air. Here you see that 2 modules have been installed, and you see the effect of the module on the wind field, on the velocity field, and also you see the effect of the concentration where there is a global decrease of the concentration in the station. Even if it's still polluted, it's a bit less polluted. And at the end, after a campaign done, once the module were installed, we have done some comparison and between the observation and the modeling. And even if the tendency are not perfect, it seems that we have succeeded in set up a methodology. It's not only modeling; it's a methodology, a full methodology, to have something that is not so far from the observation. And now we know that we could use this method for other station, maybe a bit more complex station with a larger number of entrants and so on. So now I move to the next.
You have 5 minutes more.
Yeah. So so here we are in a gymnasium. So again, it's a project by S.R.L. And actually, I wasn't aware of that, but in maybe 50% of sport gymnasium, there is no ventilation system. So if there is some ventilation system, then you just have to plug, to add filter to have better air quality. But if there is no ventilation system, that it makes sense to add something to do depollution. So in the project, we were focused on a gymnasium where there is some school using it on a large area. And there is also some basketball games. So here you may have sources, people, player in a smaller area, but a big amount of source of people on the seats. So we have done the same kind of modeling with the code Saturn, so the geometry and the mesh. In terms of hydraulic, don't consider any thermal effect. So the hydraulic is mainly driven by the depollution system, and we have tested different outlet extraction and outlet configuration as you see there. Here we are looking at unsteady, because one of the question is about time. One of the questions is how long should we use the system before the air is clean, or during a basket game, can we avoid significant increase of the pollution? So we have put some emission on the ground and also potentially on the seats, as you see here. We have added turbulence to consider the effects of the people movement. And then we have run the 3 configuration. So you see that there is we have tested different configuration for the aerobics. So here you see that there is difference in terms of where do we focus the clean air. And also here there were the idea to have not a small plane, but a long tube that's where there is clean air outflow. And here you see a picture at a given slice of the wind of the velocity field. And here you have some animation. So for the school, the idea was to look at how much time do we need to have a clean air after the kids are out. So if I switch on the animation, then you see that it's a calculation of several hours. And here, these 2 cases are only 2 hours. The idea is during a match, during a game, do we succeed in limit the increase of pollution?
You have 2 minutes more.
Yeah, I'm almost done. And you see that, yes, we have succeeded in limit the increase, and it seems that this configuration is a bit better to have no high concentration on the seats. And I'm done. So thanks for your attention. Do you have any question?